last module. This is on fuel cell application. By the way, all the previous presentations are now available with the exception of this one, which I will keep before I go today in the Dropbox. So you can access the Dropbox, everyone? And the files are all readable, the files are coming up nicely. Sometimes when you save, so our presentation today is on fuel cell application, but more so in relation to the application of the gases that come from the gasification of solid fuels, solid carbonaceous fuels. And so we'll first touch base with the very basic fundamentals of fuel cell, and then we will move more towards the end, more on the direct carbon fuel cell, and there will be, I'm hoping that I will be able to finish everything before the lunch time, so that immediately after lunch we can have just wrap up discussion and nothing else. But if I can't finish before lunchtime, then there may be 3 or 4 more slides that will be left to be discussed. So this is, let me acknowledge my colleagues and ex-students who work at the CSIRO and now also at the industry now, who have been strong partners, collaborators in our fuel cell work. So let's see why fuel cell. Okay. So this is a graph that I took from some of our own calculations. The first one, it shows the net power plant efficiency on a lower heating value basis, unfortunately. And it shows how the efficiency can be improved if you change the fuel, if you change the technology type, etc. So this essentially comes from very detailed process simulation carried out by software such as Aspen Plus. The first one, the first block there is, it corresponds to brown coal steam turbine cycle, but subcritical. So because brown coal has a lot more moisture, so its efficiency is less. Black coal is more like the bituminous coal. This is for Australian context, so that's why we call them brown and black. But brown corresponds to more like the lignites, and black corresponds to more like the bituminous coal. Brown for lignite. And it is brown simply because when it gets dried, the color changes to brown. Even though when it is fully moist, its color is black. So then so black coal has less moisture to start with, therefore black coal has higher efficiency. Then the subsequent ones are with supercritical steam turbine cycle, ultra supercritical steam turbine cycle, IGCC, you know. DICE stands for a technology called direct injection coal engine, and DCFC stands for direct carbon fuel cell, which is the focus towards the end of this presentation. So what is DICE? Okay, let me go one step back. Everything other than the black coal, everything other corresponds to the use of brown coal. So you can actually see if you go along the technology curve, if you go along the technology curve, no, it's dead. If you go along the technology curve from brown coal steam turbine to supercritical steam turbine to ultra supercritical, then you can go higher and higher until the ultra supercritical steam turbine. So that's mainly because of the improvement in the steam cycle, nothing else. Higher pressure, higher temperature. IGCC obviously gives you a little bit more because it's a combined cycle, correct. And direct injection coal engine it was a relatively new development in the early 2000s, where the diesel engines were modified to fire coal slurry directly into the engine. The understanding was that it will give rise to much higher efficiency, and significant test program did take place in Australia, in Germany, by collaborating with companies called MAN, MAN, the German company. They are the biggest, one of the biggest diesel engine suppliers. So some tests were done, predominantly short term, and my understanding is that the dice development has now stopped. Then comes the direct carbon fuel cell, because direct carbon fuel cell, it doesn't rely on the thermodynamic limits imposed by the steam cycle or the combined cycle. So its efficiency is calculated in a different way. So fuel cells efficiency is calculated in a different way, and we will see what's the different way. Okay. But the reason yeah. Coal slurry, yeah. And the coal slurry with very fine coal particles there. So there's a fair bit of coal preparation involved. Sorry? Cleaning means because the diesel engines, how the diesel is sprayed through the nozzle, and direct contact with the piston and the cylinder. So exactly the same principle. The slurry would have been a pumpable slurry with an acceptable viscosity. But the important thing is that the particles have to be fine and have to be very low in silica. So if the overall ash content is high, then obviously dice doesn't make any sense. But the understanding that they had is that Victorian brown coal, when it is dried, it has only 2% moisture, 2% ash. And then when you make it slurry, then on a per kg, total per kg basis, it is even less than 2%. So that's the advantage, perceived advantage. But whether the silica level will be any problem, that was going to be tested through the trials. Water. Water. Yeah. So, so coal slurry feeding is not new. As you have seen, some gasification, coal slurry feeding is practiced day in, day out. So that's not a problem. Slurry is used only to facilitate the pumping of the fuel and then spraying it off. Otherwise, solids feeding is a problem. So anyway, let's not focus on that one. So the calculations done on DCFC, direct carbon fuel cell, or for that matter fuel cell, and there could be a different variants of the direct carbon fuel cell. We'll see that there would be a significant efficiency advantage going from 30%, less than 30% for subcritical to about 40% for supercritical to 60% for DCFC. So that was going to be a big bonus, which prompted the sponsors to put money into the DCFC research. But we are not the only one in Australia to do the DCFC research. Others have tried and stopped. CSIRO to a reduced extent is still continuing, but all over the world, particularly in Europe as well as in North America, considerable work has gone on and still going on in the DCFC area. So we'll come to that. No, it's not an abandoned idea. Not fully abandoned yet. No, that's like PFBC fully abandoned. This one is not. Still in the back burner, and still the universities and research institutes are doing. So here in the next one, again I have copied it from one of the CSIRO papers. I don't know what happens to it. It's a brand new one. Must be getting short-circuited somewhere and losing its charge. Anyway, so if you look at that colorful one, it's a different way of looking at it. Looking at the first graph, with one exception, that here you are looking at as a function of the capacity of the unit. So the x-axis ranges from 1 kilowatt to 1000 megawatt, and y-axis is the efficiency, electrical efficiency, so the power generation efficiency. So no, they are not different. They are taken from two different sources. That's why the terminologies are different. But it is the overall plant efficiency. So when you say electric efficiency, as far as the bottom one, electric efficiency takes care of everything inside the system. So it is net. Whatever is going in as the energy associated with the coal, and whatever you are eventually getting in the form of electricity generated. Okay. I haven't used it. People have used it. I don't like it, but that's how it is. This looks good. LHV and HHV efficiency. I always make the point that HHV better represents, but nevertheless, these are all, irrespective of how you represent it, if you are representing the efficiency of all the technologies on the same basis, then you are more likely to get the relative picture, more or less. There are some differences though. Anyway, so one important message to take from here is that the largest capacity plants are combined cycle gas turbine unit or the steam turbine cycle, as we see in the conventional power generation plants. The diesel engines are somewhere in the middle range, but less than 10 megawatts. The molten carbon fuel cells are coming up. Combination of solid oxide fuel cell and steam turbine, SOFC, is 10 megawatt, and the direct carbon fuel cell is very, very tiny. Okay. So is the solid oxide fuel cell, so is the polymer electrolyte fuel cell, so is the internal combustion engines, IC engines. So important point to make in here is that despite being a low capacity unit, its efficiency is projected to be quite high. Usually you will see that as scale increases, the efficiency goes up to some extent. But in this instance, the direct carbon fuel cell, despite having at the current state of development very small sizes, its projected efficiency is quite high. And then the third box on the right is it shows the CO2 emission. Okay. So the first one is the emission at this point of time in Australia for brown coal. So the units are not there, but doesn't matter. It shows the relative values. So it's quite high currently. And if DCFC becomes feasible, commercial, then there will be a 50% reduction in the CO2 emissions. That's what is projected. So the second bar shows it. Then if you have the DCFC on coal with CO2 capture and storage, then obviously the third bar will be 0 because it can be stored. And then if DCFC with biomass and carbon CO2 capture and storage, then the carbon emissions will be negative. These are all projected values, assuming that biomass is fully renewable, and therefore that's how it is. So, so the only technology, not the only technology, but the DCFC as a technology, if used with coal and storage, then is supposed to give you a 0 emission. But if it is used with biomass, then it is supposed to give you a negative emission. So that's the incentive towards the research on DCFC. So before we go to the DCFC, let's go to the next slide as to what's the operating principle of a fuel cell. So the operating principle of a fuel cell is something that we have known from our school, that we have an electrolyte somewhere in the middle. Then we have the anode on one side, cathode on another side, and if they are and oxygen is fed from the cathode side, while the fuel, whatever the fuel is, solid fuel, gaseous fuel, liquid fuel, etc., is fed from the anode side. And if the fuel gets oxidized at the anode by some kind of an anodic reaction, then it will generate the electrons, and those electrons will then find their way to the other side through the electrolyte, which are nothing but ionic species, and will generate power. So that's the summary, that's the concept or the operating principle of a fuel cell. So to summarize, fuel gets oxidized at the anode, on the anode surface, and then it generates the electrons, and either formation of ionic species, which in that case are transported through the electrolyte to the cathode, or the formation of the compounds by reaction between the fuel and the ionic species, again transported through the electrolyte from the cathode to the anode. So at the end of the day, well, all you are doing is you are, as for electricity generation, it's only the electrons, their movements. So this is what is facilitated by the fuel cell and nothing else. So one important issue that I would like you to remember in here is that the fuel is sent along the anode side, and technically the fuel can also be an anode. So if you have a very high quality coal product, for example char, that can be the anode, that can be the fuel, even though the anode will be gradually consumed, but then you can replace it, which means you can technically you can have the anode as fine particles of individual particles of carbon. Okay. So the efficiency of the fuel cell, the way we calculate it, we'll see. But let's look at the Gibbs free energy, which is common to everything. And we know what is delta H, what is delta S, and what is the temperature. What does the temperature mean in this case? Whether the temperature remains the constant throughout, that's a different issue. For example, in coal-fired furnaces, or for that matter in gasifiers, the temperature actually varies, right? And the fuel gets converted at a wide range of temperatures, even though eventually the temperature is controlled to a certain level. But the fact is that the temperature at which different particles of fuels get converted, those temperatures are all different. So technically, I think if you are calculating the efficiency of even a coal-fired furnace, that's just the furnace itself, you'll have to take into account the temperature variation that is faced by the different sized particles. We usually don't do it. We just, as a rule of thumb, we just do it at the maximum temperature. That's not necessarily accurate, but that's how it is. So here, having introduced or reintroduced the term delta G and delta H and delta S, etc., we can define that the thermodynamic fuel efficiency of a fuel cell, assuming that all the fuels are utilized, that all the fuels that you have sent, you have fed is utilized, is defined as the ratio of the free energy and the enthalpy of the fuel oxidation reaction in this way. So the fuel efficiency is percentage wise is defined as the total delta G divided by the delta H, which if you can do a little bit of mathematical manipulation, then you can express it in terms of temperature and delta S, I mean the entropy change, but also you can express it as the function of the three terms N, E subscript O C V, and F. So we'll see what are those terms. Here, N stands for the number of electrons that gets transferred for a particular reaction. So if you know what reaction you are talking about, whether it's a gas reaction or whether it is a coal-based reaction or it is a carbon-oxygen reaction or hydrogen and oxygen reaction, you know how many electrons will be involved in that particular reaction. That's quickly can be done by having a look at the reaction itself. So we'll see that. So, and here the OCV, it stands for the open circuit voltage, okay, for a fuel cell. Open cycle voltage means when you have connected them, the current will flow, right, from one of the electrodes to the other of the electrodes through the electrolyte. So what is the voltage that you can get? The voltage that you can get will be a function of it will be a function of the internal resistance. Therefore, that internal resistance will be dictated by the type of the anodic material, type of the cathodic material, type of the electrode, and type of the fuel. So everything will give rise to a segment of resistance. So that will eventually dictate how much open cycle voltage you can get. And then of course the denominator still stays at the total enthalpy. So nothing spectacular here. So let's just look at some of the reactions that potentially can take place at inside the fuel cell at the different interfaces. So you have on the first column different reactions. Then you have in the second column the number of electrons involved. Then the third column is the total enthalpy involved. Then the fourth column is the Gibbs free energy, and typically what sort of open cycle voltage that we get at different temperatures, at low temperature as well as a high temperature. This is usually measured, that's the EOCV. And from there, if you get all of this, then you can actually calculate the thermodynamic efficiency as we had in the previous slide. Okay. So, so it all depends on the type of the reactions that you are going to effect. If your fuel cell is only going to use natural gas, then obviously the last reaction is the most pertinent. If your fuel cell is going to use only hydrogen, then the first two will be relevant, depending on where you want, to what extent you can take it, whether the product from fuel cells reactions, whether that is condensed or the product is not condensed and allowed to go out as a gas. So depending on that, the first two expressions will be different. And it's quite interesting to see. Well, if you take all the liquids, the water vapor out as the condensate, then you are recovering its latent heat, and therefore it will be, we say that the efficiency is expressed on the basis of the higher heating value. But if you allow the water vapor, which is the product of the fuel cell reaction in this instance, if you allow it to go in the gas phase, then you are not recovering it. So you say that it's done on the basis of the lower heating value. The point I'm trying to make is that if you know your reaction that you're going to use, if you know what fuel you are going to use, then you know what reaction you're going to use. Then from there you know practically everything, and the open cycle voltage comes from the experiments, and that will allow you to calculate what efficiency you'll be getting. So the thermodynamic efficiencies are actually very, very high, and the way these are defined, the thermodynamic efficiency can be over 100%, but that's an artifact of the definition, nothing else. So all you will be looking at is the headline numbers, rather than saying that how this is more than 100%, because above 100% no efficiencies are possible. But at least when the way these are shown in here, it shows the relativity between the different types of reactions that you can have depending on the type of fuel that you can put. So let's go to the next step to define how the open cycle voltage and the overall voltage is estimated. So this is how it is. The OP, subscript OP, stands for the overall sense the voltage. OCV is the open cycle voltage, and from that you start deducting all the resistances that Dr. Davis said. There is a whole lot of internal resistances. There are resistances of the electrolyte, the second item. Then then there will be resistances at the anode electrode interface. Electrode will be in the middle, anodes will be on the sides. There will be similarly losses at the cathode electrode interface, and then depending on the type of the electrolyte that you have, the ions may find it easy or difficult to diffuse through them to go from one electrode to the other, and therefore those will be accounted for. That resistance will be accounted for by that concentration polarization time, concentration polarization figure. So staying still on the fundamentals, the theoretical efficiencies of different fuels, and we will see different fuel cells, how that can vary. DCFC is the standard, the direct carbon fuel cell, and then you have the other fuel cells like the PEM fuel cell, polymer electrolytic membrane, PAFC, then the MCFC, the molten carbonate fuel cell, or the solid oxide fuel cells. So we'll see each of those a little bit later. The way it is, the estimated efficiency is set for a baseline. The DCFC's efficiency is set at 100%, and based on that one, which is the highest efficiency fuel cells of all, the efficiency drops for the other ones are calculated. So that's why you will see all of these colors. But how much each of those types will be dropping, or what will be the starting efficiency of the DCFC, that will also be dependent on what actually the fuel is, whether the fuel is solid carbon, as in the first, as in here. I hope it works now. As it is in here, or is it a natural gas, or is it some other gas, or is it hydrogen? So depending on that, because each reaction, as we have seen before, involves a different number of electrons being transported across. Therefore, the estimated efficiencies will all be different. But the point that I would like to make here is that if you are having hydrogen, or if you are having the gaseous fuel such as methane, your efficiencies can actually be quite high, even though we have to keep in mind that methane can only be utilized in the high temperature fuel cells, and which ones are high temperature, we'll come to that as we go through each and every fuel cells type. So here fortunately the data is based on higher heating value, and previously I note that there is a note that was given in here that that calculating efficiency, it is more meaningful to have HHV. So even though the figures they are not shown in the HHV, but anyway, let's I think that's something that you should keep in mind. So these are the typical performance data of a fuel cell that you can measure and that you are interested at. It can be instantaneous, it can be over a period of time, it can be over a very long period of time. So one of those, there are three different statistics that we use for that matter. One is the cell voltage, and then the other one is the voltage efficiency and how that particularly drops. Then the red one is the power density, which is extremely important, that if you don't have if you have a high voltage, but if your power density is very low, that's not going to be much use. Okay. So these are the important parameters which are measured, or rather calculated from measurements during experiments. And then when you plot, then you can see whether this is giving a good performance or not, given the choice of electrolyte, the choice of anode, the choice of cathode that you have made, and also most importantly the choice of fuel that you have made, whether the fuel is solid carbon or any liquid carbon. Liquid carbons are also possible, or for that matter any gaseous fuel such as hydrogen, such as methane, such as combination of some of the gases, combustible gases. So the overall efficiency, as we have seen, are function of all of these terms. Here, one of the important term is this F subscript U, which stands for fuel utilization, this one. So we will come to that when we discuss the individual types of fuel cell. Because as you would expect, as happens in a gasifier or as happens in a coal-fired furnace, the carbon burnout is never going to be 100%. The carbon conversion is not going to be 100%. You always have less than that. For the lack of appropriate design or poor contact between the reactants and the solids, here it is no exception. Here it is absolutely no exception. What you are feeding, what else is there in the feed, that's very, very important, because that determines the resistances that the fuels will create at the interface of the anode and the electrolyte, and that in effect will also influence your overall efficiency. Okay. So the fuel utilization factor is another very strong variable that you will always measure if you are involved in the fuel cell research. The major players in the fuel cell, say GE or Mitsubishi Electric or Fuji Electric and Sara and few others, a number of others, their designs, it's in their design of the feeding system, it's their design of the fuel cell is in such a way that there is a very good contact between the fuel and the anode surface, and that the electrolyte is also conducting the ions across, so that the electrons can eventually flow. So it is it's the different manufacturers, the way they differentiate themselves is in one of the areas is the how they ensure the contacts between the fuel and the electrodes. Okay. So that is where a big differentiation point. So please do keep that in mind. So we have a slide on, just one slide on the different types of fuels, but essentially the fuels will be what are in here. So hydrogen, so the gaseous fuels are hydrogen predominantly, because if you can get clean hydrogen, then you can do everything. Or you can, if you can have something which stores hydrogen, which can then go into your fuel cell. And a lot of the fuel cells that you can buy, these days you can buy fuel cells about $50. They have inbuilt hydrogen stored in, for example, in the metal anhydrides. So hydrogen is the first choice for the fuel cell. Then of course the natural gases. Most of the fuel cells do not like carbon monoxide except the higher temperature ones. So two ways. If it is a hydrocarbon, it's a good point, then you can have either an external reformer, or now you have the fuel cell designs where reforming takes place inside the fuel cell. Oh yes, that's right. So whether you do it outside of the fuel cell or you do it internal in situ reforming, that's up to you. So some fuel cells can allow that to happen. We looked at reforming of methane, I think yesterday. Do you remember what temperature? No, before that. So we're looking at about 900 degrees or so, 900, 1000 degrees or so. But in fuel cell, if you have an internal reformer, and if you can also put a catalyst there, then internally you can reform it with steam. Steam is needed or CO2 is needed. We have seen that yesterday. You can do it at a much lower temperature, about say 650 or so. So if you are able to do that, then what's happening is that you are able to extend the life of the fuel cell, because the electrolytes will degrade less rapidly. The anode materials, the cathode materials, the junctions, the sealing of the sealing at the interfaces, which is also very important. Otherwise leakage will happen. Those will be much better if you have, in general, low temperatures. But the guiding factor is, at low temperature, can you do the reforming? So the answer is yes, that's a vigorously researched area, that reforming is carried out at low temperature, in situ, inside internal reforming, with the help of the catalyst. Sorry? So that will directly affect your fuel utilization factor. So if you, correct. Overall, yes, that's right. So the remain. Yeah, but then in these calculations, they do not assume that fuel utilization efficiency will be 100%. In most cases, they assume whatever they can achieve. Even then, compared to, correct, factor is not 100%, is well below 100%. But that's the advantage of the, or the attraction of the fuel cells, that if you somehow, by the design of the fuel cell, if you can increase the extent of reforming higher, if you can increase it to a higher level, then obviously your fuel utilization factor will be increasing. The chances that the fuel utilization factor will be increasing, and therefore your overall efficiency from the system will also be increasing. So those are the very vigorously researched area. I was going to come to that towards the end, but good that you have raised it. But in general, then, to answer your question, hydrogen is a fuel of choice. That hydrogen can come directly, or it can come from the reforming of the natural gas, or it can come from the gasification gas with in situ shift reaction, the CO and steam giving you hydrogen and CO2, right? So all sorts of possibilities. But then the other heavily researched area getting prominence now is to feed carbon directly, rather than producing the fuel gas separately in an outside gasifier and then piping it in. If you can do it in situ, then that will be a big advantage. Similar to in situ reforming, if you can use in situ solid carbon utilization, then that will be a big achievement. And that's something that we will discuss as we go along. Correct. So here Carnot cycle, correct. Answer the question. Correct. That is achievable here. So you are not limited to Carnot cycle. You are not dependent on Carnot cycle for your efficiency calculation, which has its limits by set forth by T1, the upper temperature and lower temperature, T1 minus T2 over T1. Right. So that's the advantage, that you are not limited by the chemical thermodynamics as we know of for the efficiency. So does it make sense to everyone? Yeah. Yes, that's very much so. But that's what research is for. If you have a problem, you don't run away from it. Correct, correct, correct. Anodic degradation, so, and what's the degradation mechanism? For example, there's a lot of work being done, and the degradation mechanism can be different depending on what your anode material is, what your fuel is. Okay, so one of the person that that I acknowledged, Adam Rady. He did PhD with us and now works in the industry, and he looked at the degradation mechanism for using brown coal directly into a fuel cell. How the cell actually degrades in terms of its percentage, in terms of its percent efficiency, but more importantly, looking at where the degradation is coming from predominantly. So it's a big area. Hydrogen was technology mature. You can go and buy one, put one in your apartment if you want to, literally. So replace the cylinder, or if you have natural gas piped into your apartment going to the kitchen, it can internally former will convert it and then do it. Yes, 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 that's right. Yeah. You can buy small fuel cells, as I said, about $40, $50, where the hydrogen is stored in metal anhydride, for example, in boron anhydride, which I don't know, maybe in here, around the world. Maybe you guys can think of having a startup. Seriously, it's not difficult. If you have a low cost base in here, labor cost base in here, it makes sense to do it. Because they will be wonderful for distributed power generation, and we will see where these are currently used. You can use a small fuel cell to charge your laptop, your mobile. All you need is a fuel supply. For car as well, fuel cell cars are available. Even though now everyone is going into the battery ones, so these things do come and go. But in some cases they are mature, and some fuel cells are already available at the 2 megawatt scale. If you have a good supply of hydrogen or fuel, or for that matter natural gas, then you can. Nowadays natural gas is piped to every kitchen, or through the cylinders, whichever. Right. Okay. Okay. Yeah. But the problem there is that if you have a fuel with a very high moisture content, your LHV value, just imagine, your LHV value will be super high. That will give you an artificially inflated high expectation that my process is giving me super duper efficiency. So in the efficiency calculation, what happens? It is output divided by input at the end of the day, right? Now, when your input is in the denominator, if you give the input on the basis of lower heating value, then it is a smaller number. Just to give you an example, for our brown coal, the higher heating value is about 26 megajoules per kilogram. But when you account for the 60% water in it, its lower heating value is about 8 megajoules per kilogram. Okay. So when no, so what I'm saying is that you can do if you can do both. So if you in the denominator, if you give your, at the end of the day, if you are burning say 100 units of coal,
and it has a certain energy value. In terms of the higher heating value, it has a much higher value. In the lower heating value wise, total energy content is much lower, simply because the enthalpy is taken away by the non-condensing water vapor. So if you give the lower heating value based energy input in the denominator, your efficiency figure will skyrocket. So it's not, I'm not suggesting that it is wrong, but it is more meaningful. That's what these people say, and that's what I believe too. So what will happen? You will come to a situation where if you have two coals, one is a high rank coal which is only 10% moisture, and one is a low rank coal which is 60% moisture. You know which one has actually more energy, the high rank one. But the way it is defined, if you calculate the lower heating value based efficiency, you will see that the efficiency calculated for the high moisture coal on a lower heating value basis will be much higher than the one for the high rank coal with lower moisture content. So you really need to, if you want to compare apples with apples on the same basis, then you really have to be doing it on the basis of higher heating value. Which ones? No. So depending on, if your fuel is very good, then the electrolyte will not be contaminated quickly. But if the fuel is not good, then your electrolyte will be contaminated, and therefore its ion conducting ability will drop. So the choice of the electrolyte, and the choice of the fuel is very important. So when I say the electrolyte getting degraded, what does that mean? Say if you are having hydrogen. If it is clean hydrogen, then not a problem. But if it is not clean hydrogen, it is hydrogen, but also it has inside it ammonia or hydrogen sulfide, that means your gas cleanup system now becomes a lot more critical for fuel cell application. Then in the presence of those pollutants in the hydrogen gas going into the fuel cell, the electrolyte will gradually get degraded. And if it gets degraded to such an extent, to a large extent, then you cannot retrieve it. You cannot regenerate it. Not easy. Because the bonding between the electrolyte and the pollutant species will be very, very strong. So you cannot regenerate it to the same extent that you can regenerate the amines using steam for CO2 capture. So it's different. So for fuel cell, the gas cleanup requirements are more stringent, even though now the manufacturers are developing fuel cell design and developing electrolytes which can tolerate the species quite a bit. So, and I'll come to that as well in one of the slides. But broadly, that is the thing. Correct. Correct. So carbon can come from a direct carbon, solid fuel, or it can come from a liquid fuel containing carbon in it, but it will be not easy to take the carbon directly. So you'll have to have other means to scavenge the carbon from there and then give it to the anode where the reactions will be occurring, and then that's how it will be. The best thing is if you can develop the carbon separately outside, say from a pyrolysis process, you get rid of a lot of the nasties, you get very solid carbon, very good ones, then you put it there. So we'll come to some of the designs where I have in situ pyrolysis, and then the pyrolysis vapors going in one direction and the carbon going in. Supply is the supply and the delivery of the high quality hydrogen or high quality fuel is very different. When it is gaseous, high quality hydrogen, if it is solids, then it is the high quality carbon free of all the other masters. Any question? So we have seen this, I think the fuel utilization factor from that started all of this discussion. So let's go into that one. So we discussed the fuel utilization factor, and fuel utilization efficiency is an important factor. And that's precisely what we can do. As one of the major issues in different types of fuel cells. So here you can see that of fuel cell steps of otherwise the pure hydrogen So you have the mix of CO2 in there, in the hydrogen, even if you are using the shift reaction after the gasifier, which is unavoidable. So purely from there arose the development of these ones, because these are allowing you to use it. Okay, they can tolerate a good amount of carbon monoxide, apart from, of course, hydrogen being the major fuel, and of course the hydrocarbons. The important thing is what is the electrolyte, because now the electrolyte is going to see a lot of the polluting species which these ones are not going to see, because these are all going to see predominantly hydrogen. Okay, so that's very important. The other point that I would like you to note on is the temperature capability. As fuel cells went on being developed from the PEM, which is the most developed and available at the small scale, you can see that the temperature capability of the fuel cells have actually gone on increasing as you have gone from the phosphoric acid fuel cell to molten carbonate to solid oxide to DCFC. But they are all at their different level of trajectory as far as the development is concerned. And as soon as you start going at the higher temperature level, it then brings on different complexities, and some of those we will discuss. Yes, sure. Now it is the temperature in the fuel cell. So keep your
gasification, pyrolysis, thermochemical hat off. Okay, this is electrochemical thing. So don't think that, oh, temperature is 60 degrees, how is it going to work? No, this is electrochemistry. This is the electrochemical conversion. This is no longer thermochemical conversion, and in thermochemical, nothing will happen in those. But when you go into this, the higher temperatures, that allows you to bring in fuels which can also be in situ converted to some extent thermochemically. And that's why the fuels are now going to look different. Okay. So is that aspect clear to everyone? Yeah. Is it clear what I said? Yes, what did I say? You are not listening. The way you reacted. I'll tell that again. Don't worry. Yeah? Uh-huh. Correct. I don't know. That's a big research issue. It's a big, big issue. So can you design the fuel cell in such a way that the ash will not go into the electrolyte? Can you do that? If you can do it, then that will be a breakthrough. That will be a challenge overcome. So you have identified the problem that ash electrolyte interaction could be a problem. So now you think of what are the solutions. The solutions can be I develop an electrolyte which is tolerant to significant level of ash, or I design it in such a way that ash will be bypassing the electrolyte. There is possible, people are working on it, and we'll see some of the sketches what is ash is taking. But very good, this is an issue that that has been recognized. It is a major issue that has been recognized, and therefore research effort is going into it. Very good, very good. That will be another solution if you can do it. So that's a very outside the box kind of thinking. It's all possible. That's what the PhDs will be doing. Right. So what I wanted to mean in there when I shook you up is that it's a targeted approach. Absolutely, it's a targeted approach. Correct, correct. Correct. So ideally, if you were able to generate hydrogen cheaply and abundantly, then who would have bothered to go for carbon, trying to put carbon into the fuel cell? But unfortunately, that's still not happening in a large scale. I mean, you can do it. Solar-assisted electrolysis is possible. You can, in fact, you can actually have, you can buy solar-assisted electrolyzers and put at your home, generate the hydrogen and put it to your fuel cell. Literally, you can buy them if you have sufficient money. Not a huge amount of money, but you can actually put. All you have to do is to from time to time you have to put the water. That's it. And if the water can come from your air conditioner condensing, you can get some back there too. So it's quite important that you think that way too. But still, it is when we are talking about large-scale distributed generation, we do not have access to any method that will give us hydrogen very, very quickly. With all the solar and PVs coming in now and price dropping, maybe that will. maybe that way. So the solar collectors connected with the fuel cells, maybe that will. Yeah, that's true. Okay, so let me just give you an example. At our home in Melbourne, we have only most of the time 2 persons living. Okay, our son is not there. So we have on top of our roof, we have a panel which is just good enough on a good hot summer day, on a good hot day to generate the hot water. Now, people are putting in, with government support, 3 kilowatt system, 4 kilowatt, 6 kilowatt, 12 kilowatt systems, depending on how much money they have, how much energy they will use, they will need, and how much space do they have on the roof, and whether those are rightly positioned, tracking the sun properly or not. So these are available. So the point I'm making is that it's all becoming now distributed generation. How long they will remain efficient, I do not know. Then you will have to think of disposing them, waste disposal, waste processing. That's a different area. At some point, these things will not remain as efficient as they are at the beginning. So these huge silica containing panels, they have to be disposed in a certain way. But people are actually now designing in such a way that this can be disposed very, very easily. You don't have to just break it with big hammers and then get the silica out. There are different ways they are now manufacturing. The Germans are manufacturing in such a way that these are all taken in small pieces and then recycled back into the new panels. So out of adversity, out of need, comes all this, out of all these challenges, comes out all of these solutions. So for distributed one, I have seen people putting in even 24 kilowatt system, big house, and sometimes they actually feed back the power to the grid, and they get some amount of money back. So we get about 12 cents per kilowatt hour back if we feed any power to the grid. Not much, but at least something. We pay 100. Correct. So we pay about 140 cents per kilowatt hour to buy it from the grid. Okay, so whatever. So the point I'm making is that when these were first introduced, the government gave incentive, and the government said, okay, you can sell it to the grid at 80 cents per kilowatt. So it's huge. Yeah. So the payback period was quite low. So the point I'm trying to make is that all of this will have distributed power generation use in the near term, and these are being used in that way. And this will be, whether this will be a 500 megawatt fuel cell unit, I doubt, very much doubt, but who cares? You are not going to solve the CO2 emission problem by only a single technology. It can be a combination of different technologies, correct? Okay, so the point that I was trying to make was that here this is all based on electrochemical conversion. The efficiency is guided by electrochemical conversion. Therefore, seeing the low temperatures at the rightmost column should not ring any alarm bell. It's simply because it's electrochemical. Okay. But then as you go into the higher and higher temperatures from the top to the bottom, what that allows you is to bring in thermochemical conversion process also in the mix. And as soon as you bring in thermochemical conversion in the mix, then that allows you to use fuels which are not easy to be electrochemically converted, such as carbon. Okay. So on that note, let's finish and then let's have tea. and then we'll come back. Okay.